We're happy to have Tarun Grover, who will talk about skyrmions and the fermionic dualities. So this talk will be relatively short, so please ask a lot of questions. And also, we have a strict cutoff at 12:20. At 12:20, we should leave and go back to the hotel. Yeah, so your time. Okay, Tarun, please.
Great. Yeah, thank you so much for your very kind invitation. And everyone can hear me fine, just to make sure. Should I raise my volume or is it fine?
It's good. It's good.
Okay, great. So yeah, thank you so much for the invitation. And this work is with my amazing collaborator Xiaoyan Xu from Shanghai. And I should also thank John for asking often my stupid questions from time to time, and just, I don't know, just think I gained a lot from discussions with John. So, all right, so let's get started. So I'm one very broad qualifier. This is work in progress. There are things I certainly don't understand, and so please ask questions, and I'm hoping I will learn from you guys more than you will learn from me, because I think you guys are probably more expert on some of the stuff I'm talking about. And so anyway, so let's get started. So the broad background for this talk is about so-called Bosonization dualities for conformal field theories. So and my capital D is space-time and little d is space. So we know in 1+1D, Bosonization is a very old tool which has been used very profitably for a lot of problems, starting with this Tomonaga, Luttinger, liquid, and so on. And when we come to 3 dimensions, Chern-Simons provides a way to transmute statistics. And I'm not citing a lot of famous papers, but I want to mention is that there is this very interesting work in 1994 by Chen, Fisher, and Wu, where they argue that the 3D Wilson-Fisher CFT for the O2 model is dual to a single Dirac fermion coupled to a Chern-Simons at level half, and that's the intuition behind it came from flux attachment and using physics of Chern-Simons, and more recently, such kind of dualities have become much more, let's say, put on slight, I would say, more rigorous footing, at least in certain large limits. There are all these very interesting works, and the relations between these dualities, so-called duality web and so on, has also been kind of a topic of extensive discussions and all these works. Again, I'm not citing all the papers because there's so much has happened, but just some list of things which came to mind. And another related idea has been using part-on constructions. Suppose you're interested in some phase transition, you use 2 different part-on constructions for the same transition. That also sometimes is helpful to maybe conjecture various dualities. And all these things are not unrelated, right? I mean, flux attachment is sometimes related to part-on construction. So these are not like completely independent approaches. And also this Gitaev's part-on construction, all this, I mean, these things are related with each other. So this is a kind of, so a lot of stuff I'll talk about will be motivated from such considerations. Another perspective on similar dualities comes from quantum numbers of solitons. For example, there's this very nice work by Goldson and Wilczek where they look at fermions in the background of some smoothly varying some order parameter field and look at solitons, and solitons get some quantum numbers when you look at the fermion determinant and so on. So this is a different perspective on, I would say, I mean, at least all the developments by, I don't know, Tomonaga, Luttinger, and so on were happening in parallel with these developments, and from the point of view of quantizing solitons, for example, work by Fadib or Coleman and so on. One kind of motivation for this talk is to somehow ask whether thinking more about quantum number solitons perhaps gives some new insights into dualities. I'm not sure I will succeed at that, but at least that's one of the motivation. So similarly, when bigger than two space-time dimensions, for example, in QCD, baryons are skyrmions of some order parameter field. So this is, I'm just listing a bunch of examples. So the one paper which was kind of motivation for us was this very interesting work by Abano-Wigman from 1999, which many of you have used all the time in your work, where they listed down class of very simple looking models where fermions are coupled to some background, some order parameter field. They look at the low energy theory of the order parameter field, and they find interesting topological terms. As an example, so consider, for example, two flavors of Dirac fermions in 2 dimensions, coupled to a 4-component order parameter field, which I call V, and 3 components are N. So this is total 4. And this is the coupling. There's a gamma phi metric, Bn1 plus 1d. So you can define a gamma phi metric. Sigma acts on the flavor space because there are two flavors of fermions. When you integrate out fermions, you get a standard kinetic energy for this 4-component vector, but also a O4 Bose-Fermi term for this 4-component vector, which can also be written as SU2 level 1 term. If you think of this as V plus I sigma dot N as some SU2 matrix. And this is simply the low energy theory of the spin-half Heisenberg chain, which has an emergent O4 symmetry. So this is a way to kind of, if you like, bosonize this action of fermions coupled to some background gauge field in terms of some bosonic looking variables which have some topological term. And similar ideas were used later on to find dualities for other field theories. For example, those relevant for deconfined quantum criticality. Okay, so the two kind of, as I already kind of hinted, the 2 broad motivations for this talk are: can thinking about field theories for order parameters with topological terms can teach you something new about Bose-Fermi dualities? And secondly, when you have topological terms in some field theory, at least that's a sign of some kind of that's a hint that the system has some sign problem, fermion sign problem, because fermion determinant is not entirely positive because of this. But perhaps if we understand these dualities well enough, perhaps we can solve such sign problem by dualities. For example, perhaps we can calculate universal properties of some interesting Chern-Simons matter theory using dualities. These are the two broad motivations for this work. And before I go further, this may be just maybe a stupid comment that when we say Bosonization, it's nothing. I mean, truly there cannot be Bosonization in any true sense, right? If you have a neutral fermion on one side of a system, other side should also have a neutral fermion. So you can't have a fermion theory to a truly bosonic theory. Fermion is hidden in some non-local variables. But okay, the name is used in some colloquial sense when we say Bosonization. But it's but if you really think about it, it's not truly Bosonization. But anyway, so the so examples of let's look at some examples just to motivate further. So I made a slightly longer kind of background just to kind of, I don't know, I thought I had full 1 hour, so let me give a bit more background. So also please stop me any point, ask questions. I really encourage you. So consider as a set of examples where the order parameter space is some Sn and sphere, and let's consider different dimensions. For example, when the space-time dimension d equals n, then pi d of Sn is just z, pi d of Sn is pi d sd. So this allows one to add in the action a theta term, which is corresponding to I times theta times the space-time instanton number corresponding to this non-trivial map. And instanton number is obviously a number, it's an integer. So the theta doesn't have to be integer, but theta is multiplying this integer. But when n is d plus 1, then you're allowed a Bose-Fermi term, where you get 1 extra dimension because the way Bose-Fermi term works. And then then the topological term that can appear sometimes is I times some integer k times the area traced by this order parameter field on some sphere. So now it's the coefficient is quantized, but the term itself is not quantized. So one very famous example is this d equal to 3 n equal to 4 case when we get a O5 is a Witten description for the nail to BPSD confined critical point. However, even when n is not equal to d or d plus 1, even then sometimes this map can be non-trivial by the Sn. For example, pi 3 of S2 is Z, which leads to the possibility of so-called half term, which will be the focus of this talk. Okay, so here's one table I just made. I don't know. I'm not citing any papers. It's just things which we know of from last 30, 40 years of work, but just to kind of motivate a little bit more. So here is space-time dimension, the rows, and the columns are the order parameter field, G mod H, various spheres. So when you can state, I don't know, whichever favorite example. For example, when d equal to 1, when you get a theta term for just a quantum mechanical system, particular ring with a flux, it can be thought of as a theta term. And you can look at a diagonal or theta terms. When you go slightly off diagonal, this kind of whatever, this off diagonal, whatever this is called, is a Witten term. But in addition, there are these things which are neither theta term nor Witten terms, which are like half terms. For example, pi 3 S2. And they, I think, have been less studied as far as I can tell. So at least that was our motivation. So, and some of these things I don't actually understand. For example, maybe if you have any insight, I'll be very curious. For example, pi 4 of S2 is Z2. So what is that topological term? That means in 3 plus 1D, if you have a 3-component order parameter, perhaps there is some interesting thing. I don't understand this. So I don't know. This is not the topic of this talk, but if you have any insights, I'll be curious. And d equal to 4, S3, this is a famous QCD Lagrangian when you have half term makes skyrmions, fermions for SU2 case. Let's see. I don't think I want to go through all of them. You can stare at them and think about them. If you have if something comes to your mind, you can ask right now. But we'll be focusing on this case, d equal to 3 and 2 sphere. But I just wanted to list one example from each class just for fun. So any questions there?
Actually, I think for the pi 4 S2 equals Z2, I thought Ashwin had a paper long back.
Oh, okay. But was
that
it really
describing the fact that the Hopf soliton in 3D is a fermion?
No, that pi 4 S3.
No, it's Hopf soliton. Hopf soliton is the.
Oh, yeah. So pi 4 S3 is also is also Z2. I think there were 4-component order parameter.
But the Hopf soliton, the target manifold is S2. Yeah, of course, the Hopf soliton can be okay. See, I think in that paper they are explicitly saying that this is pi 4 S2 equals Z2, and this may be
okay.
Pi 4 S3.
Thank you. Okay, I did not know that. Okay, thank you.
Okay.
Yeah, somehow I thought it was 4-component order parameter, but okay, I am wrong. I think thanks for clarifying here. So, so what we'll do, we will motivate a conjecture for a dual of a Gross-Neveu transition based on this half term. And the idea is skyrmions are fermions in the ordered space. That's the idea. And then we will see whether we can make the duality somehow reasonable sounding, and we will run into some trouble. So, and then we will perhaps pursue a slightly different duality. So, in addition, we will pursue a sign problem-free lattice model, which can host such a phase which has skyrmions which are fermions. and we will study numerically various universal properties and try to relate them to this duality. That will be the idea. Okay, so let's keep going. So so this is a low-energy theory of our interest. D equal to 3 space-time, 2-component Dirac fermions, and 2 flavors of such 2-component Dirac fermions. So Dirac fermions are always 2-component Fermi, and we consider 2 flavors of them. Sigma acts on the flavor index, and N is my 3-component order parameter. So it's very much, this is the standard Gross-Neveu kind of action, which is called Gross-Neveu Heisenberg because of this 3-component vector. And there's an I here, don't get scared by this. This I is just, it's not like non-Hermitian Hamiltonian. Psi bar I sigma psi is Hermitian, just the way the gamma matrices here are. I think the way in 2 + 1D, if you really want to write down an imaginary time action in a proper way, this we want to, anyway, yeah, this is just the convention. So don't worry about it. Maybe you've seen it in various tables like Abanov-Wiegmann or Seinthal-Fischer. This is the same reason that this is the way imaginary time action works. If you want to write it in a nice way, easier way to write it. And so the global symmetries are SU2 flavor and U1 charge. So fermion number is conserved, and there is flavor symmetry. So what is the phase diagram we are interested in? Is a Dirac semimetal, which is just basically non-interacting fermion with some irrelevant interactions. And at some point, this interaction becomes large with this. Think of completing the square. If you, for example, if you don't want to work with this order parameter field N, you can just work with fermions and consider a term like psi bar sigma psi whole square, right? All these pulses. I mean, there are different ways to do study this transition. So you can think of that interaction strength of this psi bar sigma psi whole square as this tuning parameter, which is equivalent to this M. So, and at some point, flavor symmetry gets broken down to U1, and then you get 2 Goldstone modes, and fermions are capped out. So this is
this is simply adding V of N square, some potential.
Yeah, there are many ways to write it down. Yeah. Yeah.
And then I don't need to think of strong coupling. I can do everything with weak coupling.
I mean, the transition, real transition will occur. We are not doing some large N, so transition will always occur at some order 1 coupling, right? It's an N equal to 2. It's an order 1 N.
No, so, there are many things that are called N here. N is both the number of fermions and the scale.
Yeah, sorry. Yeah, I mean NF equal to 2. Yeah.
Okay, the number of field is 2. And N vector is a 3-component symmetry vector, realizes the global SU2 linearly.
Right.
And then you can add the potential V of N vector square.
Right.
Then you can see this transition occurring at weak coupling.
Yes.
I'm asking whether I'm going to lose anything by doing it, because I prefer to think everything in weak coupling rather than.
Our understanding is you do not lose anything.
I'm sorry?
Our understanding is we do not lose anything if we work with a linear, the non-linear sigma model. Yeah.
So it's important that I do not do that.
No. I'm saying we do not lose anything. I think it should be fine. You'll be fine. That's what I'm saying for the critical properties. And some of that intuition comes from various. For example, if you do epsilon expansion or large NF calculations with either, you can formulate this model in 2 different ways, either this way or using the way you mentioned. And to whatever order, I don't know whether in non-perturbative proof, but to order, let's say 5 order in epsilon expansion or order 1 over N cube in, or 1 over NF cube in, people find same exponent. So at least that's build some confidence that it doesn't matter whether you write it this way or the other way. But I don't have a general proof, but that's my intuition that it should not matter based on all the other examples we know. All right, so here comes the main step. This is also, I mean, this is you might have seen this Abanov-Wiegmann paper. You take this action, introduce some probe fields also. Let me just do them just for fun, and integrate out the fermions to obtain a effective theory for the order parameter field and the response fields. So AC, AS are not fluctuating gauge field, they're just response field, and that's really my general notation. Capital letters will be probe field, and little letters will be fluctuating dynamical gauge fields. So you get this action. So what are the terms here? M is this, so the new variables here are H. H actually is a Hopf invariant, which can be written in the following way. First, write down, so the first introduce this topological current, this skyrmion current. So this system has skyrmions because we are in 2 space dimensions, like this picture you see here. And you can define a skyrmion current. So write the skyrmion, which I call J mu topo, write a skyrmion current as some curl of some little gauge field A. And from there, you can define a Chern-Simons-like term. So I pi times Hn will become a Chern-Simons term at level 1 for this little gauge field A. So that's first term. Second term is the coupling of this topological current to this AC, the charge gauge field. That term also appears. And the coefficient is 1 here. That's important. Since I'm working with electrons which have some charge, I've set that charge to 1 because of this coefficient 1 here. That's my normalization. That tells me that, so with that normalization, this term means that skyrmions carries charge 1. So the same electrical charge as the electron psi. Let me call this electron this psi because they are, they are not coupled to any dynamical gauge field. So then then you get this additional term, the mixed term between AS and AC. Okay, so what is the meaning of these terms? So the first term is skyrmions have fermionic statistics. Again, I'm choosing the number of. It's important that the number of flavors of fermions here is just 2. If it were 4, like in a graphene.
I'm totally lost. What is big N? N is a 3-vector?
Yes.
Unconstrained?
Yes.
Okay, but including the point N equals 0?
N is a 3-component vector, right? Sigma x, sigma y, sigma z, acting sigma x, nx, sigma y, ny, sigma z, and z.
Okay, so including the point N equals 0.
Including the point.
The Lagrange space of big N is R3. It's not S2.
Oh, I'm n square. Think of n square as 1 for this section. Yeah.
But not for the previous one.
I mean, you can set everywhere n squared to 1 if you like.
It's a different model.
As I said, if you're only interested in the critical exponent, it doesn't matter whether you work with a linear model or a non-linear model.
Well, I think it actually does matter because the linear model makes sense. The non-linear model, as it stands, is not renormalizable. So that's why I asked you before, and you kept saying that N is a 3-component order parameter. And I don't see whether I could.
It's hard to define this pi to S2 mapping, right? If you want to work,
it's not hard, it's impossible.
Yeah. So then I don't want to do that. I want to work with n square equal to 1.
Okay, so you're not, the option of adding a potential V of n square is excluded. I asked you earlier whether I could take the original Lagrangian, add V of n square, and you said that I'm not going to lose anything.
You won't lose anything about the critical exponent for this transition. That's what our understanding is. But
But the discussion here on this slide doesn't make sense in that option with that option.
Yeah, I don't know how to think about these terms without setting n square equal to 1. Yeah.
Okay.
Right. Okay. So these are the anyway. So yeah. So these are the 3 terms. So the meaning of these 3 terms is that skyrmions have fermionic statistics. and they carry unit charge, and then the third term, suppose you choose, for example, choose some directional symmetry breaking in the ordered phase, let's say along z direction, but this implies that the ordered phase is a quantum spin Hall insulator. You should not think of it as a really antiferromagnet, really, but
I'm sorry, I think this point is actually quite important. So if you do not constrain big N to have modulus 1, the system is as you describe. It has a U1 of electron, global U1 that rotates psi, and there's an SU2, and you might need to mod it out by some Z2. If you also say that N is constrained to have modulus 1, then the system has another U1 symmetry, which I guess you're interpreting as skyrmion number.
No, skyrmion number conservation is the electrical, that's a whole point of this equation.
But that's exactly why I don't understand, because if you add to your action the constraint at the top of this slide that N square is 1, then I see two symmetries in the problem. One rotating psi by a phase, and then there's another one, which is a skyrmion current.
No, skyrmion current conservation is the electrical. Think about it. Take the famous duality between boson vortex duality, right? So the topological current on one side becomes the particle number conservation on the other side. This is the same thing here. In this effective theory, there are no fermions anymore. The topological conservation is precisely your U1 on this side.
Okay, I'm trying to understand the top line of this slide. This is your starting point.
Right.
Okay, and I'm comparing two theories. One has a potential V of N square, and the one I just substitute N square equals 1.
Forget about it. Okay, can I interrupt? Sorry. First of all, don't do N square equal to 1. Set N square equal to 1 everywhere, right? So let's look at the symmetries first.
I'm only saying there are two options. So let's examine both, because I think you're jumping back and forth between the two.
Okay.
With option 1, the symmetry is as you described. There's an SU2, there's a U1, and maybe we need to mod out by Z2. There's no other U1. If you take, on the other hand, the Lagrangian at the top of this slide, and you constrain big N to have modulus 1, then I think that your system has two U1s.
No,
one
it does not.
Fermion, and the other is the skyrmion current.
No, skyrmion current conservation is the fermion current conservation.
Sorry, I think I can make a comment that will clarify the apparent disagreement. I think Tarun is thinking of the N field as arising from a Hubbard-Stratnovich transformation starting from a quartic self-interaction of psi. So I think the theory that Tarun actually wants to study really only is made of electrons. And then in order to help understand the psi bar sigma psi squared self-interaction, he integrates in this N field. And so from that starting point, the skyrmion number of the N field isn't independent.
Exactly.
From the electron number.
Yeah, I have only electron.
With that, if you do that, then you will also have some kind of a V of N square, and I would have no question. That's why the first thing I asked was which of the two pictures you have. And what you say, John, is that there is a third one, which we can soon discuss whether it's the same or not, where there is no N at all, but there is a psi to the fourth term. And I have no problem with that. My problem is with the Lagrangian at the top of this slide.
Yeah, I don't have a great answer, but my understanding of this is that the starting symmetry as U1 charge times SU2 flavor. This system has again SU2 flavor and a U1 charge, which is a topological current. And topological, I'm identifying the topological current with the
line.
Sorry.
Where on this slide is N of modulus 1 and when isn't it?
It's everywhere one, let's say, yeah.
But except the top line.
I prefer to keep everywhere it equal to 1. Yeah, even in the top line.
If you include everywhere, then there is also there are 2 U1 symmetries.
Why?
Because they're there.
No, I mean, physically.
This question of mine is not new. This question was discussed already in the early 80s in the context of the Skyrm model. And there was a question, what if we also had the baryon as an elementary field? So it would not be there's a skyrmion that comes up, but we can also add the baryon as an elementary field. And the conclusion there in the early 80s was this is wrong, because then you have 2 U1 symmetries for baryon number. One coming from the nonlinear model, and one coming from the fermion that you put in by hand. This was order of magnitude 40 years ago. Maybe I'm off by a year or 2. And it's the same issue here.
So isn't the resolution that the independent symmetries are broken by terms that Tarun didn't write down to some diagonal combination?
There isn't anything local with n that you can write down that will do the job. There's no resolution, and there's a deep reason why there is no resolution. There is a linear model with n, which is described by the top line plus v of n squared. That's a good model that you can study. Then there's another model with you assume that n gets an expectation value. You integrate out, then n will be constrained to have magnitude 1. This gives mass to the fermion, and then you integrate out the fermion and the longitudinal mode of n, and you end up with a nonlinear model without the fermion. And surprise, surprise, the baryon number of the original symmetry, the fermion number of the original one, becomes the skyrmion number in the nonlinear model. This is the story I understand. But you're kind of trying to eat the cake and have it too, and that you cannot do.
Yeah, I don't have an immediate answer, but here I do want to think of the topological conservation is the original, because I'm identifying the electromagnetic current with the topological current, because skyrmions are very charged. So from my point of view, at least the picture I have in mind is in a real system, they are electrons. I don't know the answer to your question, but picture I have in mind is they are just electrons interacting with each other. Let's say some purely electronic model, which has some interactions, and then interactions lead to an ordered phase. And physically, we do talk about skyrmions even in systems where we don't, I mean, just in I don't know, in real experiments, people do see skyrmions. You may say skyrmions are not well defined because you're not setting mod n to 1 or something. But I mean, in a real system, they are, I don't know.
But you could say the same thing about QCD. There are fundamental fermions, and there are baryons made out of them. And then there's another Lagrangian with the field U, which is nonlinear model. And there's a skyrmion that comes out of this Lagrangian, which is identified as the microscopic fermion.
Right.
But you do not write the Lagrangian both for the nonlinear field U and for the fundamental baryons. You can't do both.
So we should move on because we have a cutoff. So let's leave it to discussion section.
Okay, yeah, I think I need to think about this more. So I don't have a great answer. So, okay. So what we will do next is to formulate this this action in terms of n, in terms of the CP1 model, where the half term is basically a Chern-Simons term at level 1, and the topological term, I mean, this coupling to external gauge field A becomes just a mixed Chern-Simons term between the internal gauge field and the probe gauge field. So at least the broad intuition behind this duality is that there could be 2 different scenarios. So just going back to this action here, skyrmions, the picture I have in mind is they are in this purely electronic system. There exists this order parameter field where and which has the skyrmions, and skyrmions carry this electron number, because essentially the picture is this texture is binding an electron. At least that's a physical picture, that you have some skyrmions which are bound to some electron. That's why they acquire this charge. And there could be two different ways this transition can occur. The lowest energy excitation, which carries the quantum numbers of electrons, could be a bare electron which is not bound to a skyrmion, or it could be an electron bound to a skyrmion. There are these two possibilities, and if these transitions if this transition has a unique universality class, then these two ways of thinking about transitions purely in terms of fermionic degrees of freedom, where you condense some psi bar sigma psi, or working in terms of some CP1 Chern-Simons theory, they should be one and the same transition. So if you assume this uniqueness of this universe for the transition, so that's the kind of intuition behind this conjecture I would like to mention about duality between the standard Gross-Neveu Heisenberg critical point and some CP1 Chern-Simons theory. Again, like in other dualities, one would like to think these are two. When you say these two things are same, here we have two fixed points which are both gapless: free fermion fixed point and this Gross-Neveu Heisenberg fixed point. And both of these are gapless fermions. So one would think there's an RG flow between them. So again, one would like to think that there's a quote unquote a Gaussian fixed point for this Chern-Simons theory, which flows to some Wilson-Fisher fixed point, and very much like these other dualities. Yeah, so this, I don't understand how to think about this Wilson-Fisher fixed point. I don't have any understanding because it has this emergent O4 symmetry. How to see that from this action, I don't know. This O4 symmetry arises because we write fermions in terms of Mariner fermions. You see that the terms which make this O4 down to SU2 times U1 are irrelevant. So I have no idea how to see that from this picture. But at least let's try to at least identify some of the operators, see whether they make sense. So this electron in our neutral fermion, whatever this is, of course it carries charge, but it's not able to any fluctuating gauge field. We identified as a flux charge composite of this CP1Z and a monopole which carries 2 pi flux of this little a. You can check because of this level 1 Chern-Simons, this precisely has the same quantum number as the electron. It's neutral under this a and carries charge 1 of this capital A. And you can identify the order parameter psi bar sigma psi at z dagger sigma z. But the most tricky part is how to identify psi bar psi. This term is not allowed by symmetry in our theory by time reversal. I'm assuming time reversal symmetry, so this term is odd under that. And the most naive guess is it's, because of the Chern-Simons term, time reversal perhaps becomes particle hole under duality. And does that make sense? So then psi bar psi perhaps is minus z dagger z. At the very least, one would want to prohibit a term which is like boson mass in our theory. So even if we don't know this precisely, we would like psi bar psi is dual to something which has the same symmetries as z dagger z. Perhaps it's some nonlinear function. We don't know. So let's see what happens if I just take this nice suggestion. So if you draw this phase diagram in this interaction and this mass plane for the fermion theory, then you get these phases like Goldstone mode phase and then gap phase with Hall conductivity. And in this theory, if you do the similar analysis, you recover at least, okay, I don't know how to solve this theory, right? It's a complicated theory, but at least if I use some mean field like intuition, interaction are trying to condense this object. When these interactions are large, you perhaps think expectation value is taken by this. This is just mean field theory. I'm not making very rigorous, but and then you can also go to the phase where bosons are gapped out when t is negative, and you calculate the Hall response. It precisely matches the Hall response here. But we run into trouble if you consider the different sign of the boson mass. You actually find this whole thing becomes Goldstone mode phase. because the way here Higgsing occurs, Higgs effect does not eat up all the Goldstone modes. We are left over and so it does not match. So this mapping cannot be correct. So we don't understand actually what's the mapping of psi bar psi to z dagger z. One naive guess is perhaps it's some nonlinear function of z dagger z and perhaps even of some monopole operators. We don't know. But okay, anyway, so this is not very satisfactory, but that's what we have so far. So you can ask, can one perhaps postulate some a different duality for this Gross-Neveu transition, which is perhaps more, let's say, more believable, at least, or at least we have some other evidence, let's say, for these dualities. So then let's use this Aharoni dualities, or I mean, I don't know, there are several people contributed to this. I don't know what it's called, but let me use the word Aharoni duality just for mnemonic. So there's this duality. One of them is where you can get basically neutral fermions. For example, if you take this duality and set k equal to 1 and nf equal to 2, then you get fermions coupled to some probe gauge field, free fermions, and dual to some non-abelian theory of complex scalars, coupled to some arbitrary, n is the color n. So n can be arbitrary, but I'm setting nf to 2 and k to 1 in this duality. And this duality, at least there have been arguments made in various limits, right, at large n and so on. So perhaps this duality is correct at small n, we don't know, right? But let me assume that duality is correct at small n, which is a conjecture, and try to use this duality to now propose a duality for the Gross-Neveu-Heisenberg transition. So in this original works, most of the time people are thinking about Gross-Neveu-Ising transition. What I mean by that is they are thinking of a transition where there is a term which is like this V term, not this U term. So, and then there is argument that the Gross-Neveu fixed point flows to free fermion fixed point, which maps to Wilson-Fisher to Gaussian to Wilson-Fisher flow on the other side. But we can expand this parameter space by adding terms which we want. We don't want to break time reversal symmetry spontaneously. We are not interested in this V term. We are more interested in this U term. But you can do that and introduce some part-on construction for this quantum spin order parameter, which precisely maps onto this matter content here. You can write on n as some trace phi dagger sigma phi, where phi is, think of phi as a matrix, which is nc times nf matrix, and nf is 2, and so on. So if you play this game, then at least it's reasonable to suggest such a RG flow where the usual duality, which have been discussed in the past, correspond to this flow on the left-hand side, where you have a Gross-Neveu-Ising critical point. On one side flows to the free fermion, other side it flows to the time reversal broken phase. This is the kind of stuff people have at least conjectured. Here we add this additional direction which tries to break the flavor symmetry spontaneously, where u is much bigger than v on this side, and then you have the transition of our interest, Gross-Neveu-Heisenberg, and so if you really believe this duality and believe in this operator identification, then this follows. I mean, maybe this duality is not correct at small n, we don't know, right? But at least these expanding this parameter space and thinking about these dualities can actually provide more checks on this duality. Basically, I'm just asking, consider different patterns of flavor symmetry breaking and so on. And then, because we know that the main point is exponents of this transition are known from numerics, as I will discuss soon. And perhaps if you have some reasonably believable, some 1 over n calculation to high order, then you can check some of these dualities, hopefully. So, so if I contrast this with, so now we don't run into trouble if we simply identify psi bar psi with minus trace of phi dagger phi, you get the same phase diagram as that for the fermionic theory. Again, I want to say that it doesn't mean that this original CP1 duality is incorrect. It just means perhaps we don't know how to identify psi bar psi. So psi bar psi to z dagger z perhaps is just the wrong step. We don't know. So I won't run into all the details, but one point is because they're non-abelian gauge fields, there are enough degrees of freedom to eat up all the Goldstone modes when you Higgs phi. That's the difference between this abelian versus non-abelian theory. So in the non-abelian theory, Higgsing eats up all the Goldstone modes and gives you a fully gapped phase. And also important point which we use is that U1 Lagrange and Simon's theory does not have any topological order, which is also important here because when you gap out phi, you get back maybe up to some integer quantum Hall state. That's we can always tag on that on both sides. So they are all the response functions match. So so how much time do I have actually?
So you have 25 minutes for your talk and for questions.
I didn't hear.
25 minutes for your talk and questions.
Okay,
So
great.
So 25, okay.
Okay, so I will try to finish in next 10-15 minutes. So the okay, so far at least okay, I modeled a couple dualities, one with the CP1 Chern-Simons, other with this non-abelian complex scalar coupled to some UN gauge field. And the question is, can one simulate these theory, the fermionic theory itself in some lattice model? So we would like a SU2 flavor symmetry which is on-site and only two components two component Dirac Fermi on two flavors. This cannot be done in 2 dimensions really, because I don't know, there's the same kind of obstruction as most boundaries of SPT faces. And this theory was actually discussed in the context of one specific SPT phase by Chong Wang and Senthil in 2014. So one option is to study this 3-dimensional theory fully by this 3D SPT phase. That's hard to study numerically, so we won't do that. But even if you try thinking of doing that, the main issue is if you directly study such theory, the fermion determinant is not positive because of the Hopf term. So we'll run into sign problem. So there are two issues: how to put it on some lattice. Second is how to get rid of the sign problem. So the quote unquote strategy is that look for some other model, perhaps, which is not like directly simulating what I wrote down earlier, which has same symmetries as this model and same phase diagram. So it turns out there is this work by Lang and Loitley in 2018, which turns out they have a model which has the same symmetries as our model and same number of flavors of fermions and so on, which has this same phase diagram. So that at least gives a hope that perhaps one can study that model to understand universal properties of this critical point, and perhaps study in a bit more detail. So their motivation was not anything related to skyrmions or duality or anything. They were just, I think, interested in Gross-Neveu Heisenberg transitions, and this was the simplest case. One can find the smallest number of flavors of fermions, which admits of the transition. So so we will borrow their model and study it. So the model introduced by Lang and Loitley is basically so how do they not run into trouble with regularizing a 2-component fermions with 2 flavors in 2 dimensions? So they really make it's really strictly 2-dimensional because they consider non-local hopping. So this goes by the name of slack fermion. So basically take a Dirac fermion action at low energy k dot tau. Tau are your gamma matrices, sigma is the flavor index. And so A and B are acted on by this tau matrix. So you can think of that, they become the Dirac spinor indices, and sigma is the flavor index. And if you just Fourier transform k dot tau, you get long range hopping. So that's what they did. So this is somehow it's a well-known technique in high energy physics. I think this was introduced some time long ago. So because you can't really gauge, coupling these long range hopping models to gauge fields is fairly tricky. So that's how actually, that's my understanding, that's how you evade various issues with anomalies which arise when you couple things to gauge fields. And the interaction term they have is interesting. It's nowhere it looks like it should do what you think it will do. I mean, what you want it to do, but it does if you really study it. So it has some funny looking interaction. In fact, if you naively take the low energy limit of this interaction, it looks like it generates even non-relativistic terms like psi dagger psi whole square, but somehow those terms become irrelevant at low energy. Somehow that's our understanding based on the phase diagram. So yeah, but overall seems like one does get lucky with this model. And so let me not get into this slack fermion, but these are very fairly tricky objects. You're looking at this systems which almost like chiral fermions. But anyway, I think I don't want to get into details of this. So this is figure from Loity and Lang. They did find a transition where on one side you have a gapless Dirac fermion up till some critical point, and then after that you gap out these fermions and give expectation value to exactly same operator which we want, psi bar sigma psi in the low energy theory. And we confirmed this is Xiaoyan's data. We find exactly same physics, and there's a critical point where there's a crossing. This is some structure factor normalized for the order parameter. And the interesting thing is to look at the symmetries. So one point I would highlight is the symmetry of the fermion density is precisely same as that of the skyrmion density, which is what we would like for this our story to make sense if we identifying skyrmions with fermions, and it does work out here based on all the symmetries. So okay, so one question you can ask is, does this model really you're doing some weird this so-called slack fermions, which kind of shady in some sense, right? You're studying non-local hopping of fermions. Sounds crazy. I don't know. We should trust everything that comes out of it, but at least when you start thinking about it, but it does give correct critical exponent based on all the history of last 30 years. So but what about topological properties? For example, our skyrmions in this theory are really fermions. I mean, do they behave like fermions? So one thing you can do is to consider this adiabatic process where a skyrmion anti-skyrmion pair is taken out of the vacuum, and one of them is rotated by 2 pi, and finally annihilate them back to the vacuum. So we did this calculation with this slack fermion regularization to see whether it works or not. Whether it works meaning that we get the expectation, we get the same answer as we expected based on low energy effective field theory with -1 sign. So one has to compare it with you can't just look at fermion determinant. That has no meaning, right? You have to compare some ratio of two processes. In one of them you rotated a fermion or rotated a skyrmion, other case you did not. And so there is some work involved with all that. So I can't get into much detail, but you do that, and you can argue that you can cancel out the terms, the local terms, only leaving some global term. And then we find that these two processes where you rotate versus not rotate of skyrmion have a -1 relative sign with respect to each other, which matches with our intuition that skyrmion is behaving like a fermion. Okay, so let's now go back to some of the things I motivated earlier from the duality perspective. At least we want to think about, despite all the discussion we had earlier with Nadi, I would like to think of U1 charge. My U1 charge symmetry is precisely the U1 topological corresponding to skyrmion number. So at least the one conjecture would be in this same model, and not forget about any duality. Take this fermionic model. You can define some skyrmion density locally. Look at the correlation functions of this skyrmion density in let's say in the time direction or space direction. They should match the correlation functions of the fermion density. So the skyrmion and fermion density should have same correlation functions. At least exponent should be same. In fact, and if you can, in some sense, define this prefactor, which is this central charge Cj, that should also match. That's hard to define on lattice because of lattice cutoff and so on. So we did not attempt to do that. That's a bit tricky. But at least if you could do this faithful calculation and in some analytically somehow, then it should match. That's at least the prediction of this duality. So the fermion density correlators look like 1 over r to the power 4. It's a conserved charge, and the skyrmion density correlator is also very close to 4. It's a very complicated calculation because they're looking at some very high order correlation functions. N dot dxn dyn is already 6 fermion operator. Then you're looking at 6 fermion times 6 fermion, 12 fermion operator. When you do contraction, big contraction, they're about 2,000 terms. So it's up to, I mean, it's really Xiaoyan's heroic numerics that he wrote a Mathematica code to interface sampling these terms with QMC, and it's a crazily hard calculation. I know it's bad manners to boast about how hard a calculation is, but it is hard when it's all Xiaoyan's work. And so at least you get this reasonably, within some accuracy, it looks fairly close to 4 again. But about identifying fermion with monopole. So we can look at a scaling dimension of the fermion operator, the anomalous dimension. It's about 1 point, I mean, forget about it. Let me just talk about scaling dimension is about 1.1. This is from Loitley and Lang. So one would like to compare it with the dressed monopole operator in the CP1 Chern-Simons, if you believe this duality. Or in this other duality again, the Aharoni-type duality, again, there's a similar story. But for the CP1 Chern-Simons theory, people have calculated a monopole scaling dimension that at large n. So you really can't, I mean, take it literally, but you can't really compare it. But okay, at least at the leading order, it's worth looking at the numbers. So this is work by this Chester et al. And if you plug in the numbers at n equal to 2, you find 1.06. But don't take this, it could be just a coincidence, right? It's some large n calculation, you're comparing with some exact calculation, so it's not, but at least it's somewhat interesting that numbers are close. And then what about time reversal? I mean, this titles are just slogans just motivating the duality. They are not, I'm not like checking everything, right? I can't check both sides. I can only do numerics on one side, but I'm just taking the motivation for some of the data here. So the psi bar psi is an important operator in these dualities. For example, if you, in this Aharoni type duality, delta psi bar psi is 3 minus 1 over nu, right? Nu is the correlation n for the bosonic theory. So we also look at this exponent psi bar psi in our numerics and obtain scaling dimension. It's whenever scaling dimensions are large, they are harder to estimate because you're looking at some tail of some, I don't know, some correlation function. So the error bar is always a bit large, but it turns out to be about, it's a little bit bigger than 2, the scaling dimension. So should we compare it with some Chern-Simons theory? I don't know, because it's again, all the setalities I earlier mentioned, we don't really know what's a dual of psi bar psi, but if you just naively look at the energy operator in this dual theory, it's scaling dimension at some large n, and you set n equal to 2 or so on, and then you get 1.5. Again, I'm not sure why this is the most accurate way to think about it, but at least this is accurate, more accurate than this large n calculation, let's say. So if in future there's if in future there are more accurate calculations for the dual, that will be, then one can revisit, look at this numbers and check. So the another thing which is of somewhat interest is to, whenever you have boson and fermion dualities, if you believe they are the same, then their free energy on X3 is same. So you can ask about this F-theorem F, compare it. So this is if you look at this is basically the entanglement, subleading term of the entanglement for a circle, and this decrease under RG between 2 fixed points. So let's look at this Gross-Neveu Heisenberg fixed point at large n. We don't know how to calculate this numerically, so we don't know, but we can only look at some large n calculation, set n equal to what we have, and try to estimate it. So we find about 0.48 for this Gross-Neveu Heisenberg using fermionic language. If you work with the CP1 Chern-Simons, and again use some large n estimate, the only interesting point I want to make is there's this interesting law correction that comes because of topological degrees of freedom that actually brings the number somewhat closer. If you had only leading term, because this number could have been actually negative depending on levels and so on, but in this case, it's such it kind of increases the value compared to the free scalar, and it kind of, it's not super close, but but if you look at some of the other dualities, it's actually much worse. The dualities which you believe to be true, but here at least this term helps. again, I'm not trying to attach too much importance to this large N calculation. It's just to get some intuition how numbers are. So so I think that's about it. So so the Hoff term suggests a duality for this Gross-Neveu transition, and there is a sign problem free model that hosts such a transition for this, which sounds pretty remarkable, because you would think that Hoff term precisely makes it impossible to have such a model which has no sign problem, but it exists. And we can look at universal exponents corresponding to various operators. And if you believe this duality, at least the one Haroni type dualities are perhaps more believable, then at least there's a prediction for this Chern-Simons matter theory based on the numbers we calculated, and also Loic-Lee-Lang's paper. So, and then I already mentioned, I don't understand several things like operator matching for fermion mass, we don't know. And it also suggests some interesting calculations for the Haroni type dualities, where you perturb by this Gross-Neveu type terms like psi bar sigma psi square, and I think that's a non-trivial calculation to be done analytically. But about 4D generalization, again, you can ask, again, these skyrmions can be fermions in 3+1D. Again, you can ask similar questions. So I don't have much to say about that, but that's about it. And yeah, thanks for your patience, and yeah, ask any questions you may have, or yeah, that's all.
Okay, do you have any questions from the audience? Okay, any question on Zoom? Okay, then we should stop here. Let's thank Tarun again.